Hi guys, in this video we're going to solve three problems. Problem 15.5.004, 15.5.005, and 15.5.006 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. Now for each of these we're given a vector valued function and we're asked to match the vector valued function with its graph. So what I wanted to do was share the graphs with you, but I also wanted to talk about how to graph these functions if it wasn't a matching problem, but instead a problem where we were just asked to graph R of U and V in three-dimensional space. So that's the plan. And here are the graphs. Now for the variations that you will see on WebAssign, the graphs will be shown in a different order, but I think you can see that these 6 graphs are the same as these 6 graphs, just in a different order. And then the same is true for the next one. I can scroll down, there we go. But again, we're going to focus on just graphing those. And then once we have them graphed on paper, we will choose this correct graph from these lists, or this list that is just repeated 3 times. Okay, so for the first one, if I want to graph this, basically what I'm going to do is try to eliminate the parameters u and v and write the equation of the surface entirely in terms of x, y, and z. We call that writing the rectangular equation of the surface. And it can be done relatively easily. We just have to remember a few things. Now this is our x component, so that is x of u and v. Our y component we can think of as y of u and v, and our z component is z of u and v. So I would write those down. If you want, you can drop the dependence on u and v just to make it a little simpler. We have x equals u times cosine of v, y equals u times sine of v, and z is equal to just u. Now, when we're graphing plane curves or space curves, R is usually a function of t, and we would typically solve one of the equations for t and then substitute into the other equation or equations in order to find some relationship between x and y, or x and y and z. This is similar, but things get a little tricky with trig functions. If I were to solve this for v, I would end up with an arc cosine of x over u as my v. And if I substitute arc cosine of x over u for v here, I see that y is equal to u times sine of the arc cosine of x over u. It doesn't get simpler, it gets more complicated. So whenever we see those trig functions, whenever we see sine and cosine, we're going to use our Pythagorean identities to get rid of those functions, provided that they have the same angle, and these do. They're both cosine and sine of v. So we know from trig that sine squared of v plus cosine squared of v is equal to 1. It's actually true for any angle, but it's also true for v. And with that in mind, I will solve this equation for cosine of v and this equation for sine of v, and then I will substitute over here, and that will get rid of my v's entirely from these equations. And so let's do that. I want to get cosine of v by itself. I'll divide both sides by u. Over here, if I want to isolate sine of v, since it's multiplied by u, I will divide by u on both sides. And then I will substitute over here. We've got sine squared of some angle plus cosine squared of the same angle is equal to 1. And sine turned out to be y over u. Cosine of v turned out to be x over u. And if we simplify, and I will write that in the reverse order because we're used to having x come first. We have x squared over u squared plus y squared over u squared equals 1, just squaring that numerator and denominator. And then in order to make this look even simpler, I might multiply both sides by u squared. Or you can think of that as multiplying every single term by u squared. This times u squared would just give me an x squared. And then this second term times u squared, the u squareds will reduce. will give me a y squared, and we'll have a u squared on the right-hand side. So we have eliminated v. The v's are gone. We know that x squared plus y squared equals u squared, but we don't, we have not yet eliminated u. But that's okay. We're trying to find the equation of a surface that involves all three of our variables, and we see that z is equal to u, so we can substitute that in. Then we have this, x squared plus y squared equals u squared, and u is equal to z, so that's z squared. And we can subtract z squared from both sides if we want to. And that is the equation of a cone centered at the origin with an axis of symmetry that is parallel to the z-axis and is actually equal to the z-axis in this case. So my graph will look like this. As v takes on a range of values, we go around and around a circle. As u takes on a range of values from negative infinity to positive infinity, our z values go from negative infinity to positive infinity. Of course, I can't draw the whole graph, but that's what part of it looks like. We've got that double napped cone centered at the origin. So that is 15.5.004. Turned out to be the double napped cone. Now, the next one, 15.5.005, has this, is represented by this vector valued function r of u and v. And I believe on the WebAssign website, it's listed this way: u times I hat plus 1/2 times the quantity u plus v, closed quantity, times j hat plus v times k hat. I still prefer component form, so I wrote it like that. This is my x of u and v. That's my y of u and v. And the last one is my z of u and v. So the first thing I will do is I will write that down, and I tend to drop that dependence on u and v to make the equations look a little simpler. And then remember, we're trying to find one equation that relates all three of these guys to each other. Well, actually, it's not too difficult to think of what that equation would have to be. And we see that x is equal to u, and there's a u in the equation for y, so we could replace that u with an x. And there's also a v in the equation for y, and v is equal to z, so we could replace that v with a z. So we're just going to take this equation and substitute. Y is still there. We have 1/2 times u, which is x, sub that in, plus v, which is z, we sub that in, and that is our equation. Now it looks, or maybe it's not obvious what that looks like. I might multiply both sides by 2 to get rid of that fraction, and then maybe subtract the 2y from both sides, just so that it looks more familiar. Now I think we can all see that that is a plane. You've got a constant times x plus a constant times y plus a constant times z equals some constant. Constant happens to be 0. So we have a plane, and it turns out when x, y, and z are all 0, well, we get 0 here. So that means x or y and z equals 0. That's the origin, is on that plane. It's one of the points on the plane. Now, typically when we want to draw the plane in three-dimensional space, we often draw the first octant portion of the plane by letting 2 of the variables equal 0 and figuring out what the third variable would have to be. But if 2 of the variables were equal to 0 here, the third would obviously be 0. So we've got to do something else in order to sketch this plane. One way you could do that is you could say, okay, when x is equal to 0, what does that trace of our plane look like in the YZ plane? That's way back here where x is equal to 0. Well, then we would have 0 equals negative 2y plus z, or if you add the 2y to both sides and then just sort of switch the sides, not sort of switch the sides, actually switch the sides. You would have z equals 2 times y. So when y is equal to 1, z would be equal to 2. And when y is equal to 2, z would be equal to 4. So that's in the xy plane. We would see something that looks like this. And of course it would continue, but it's almost lining up with the x-axis. So I'm not going to keep drawing that. Now let's see, when x is equal to 1, we have 1 equals negative 2y plus z. So then we would have z equals 2y plus 1. So when x is equal to 1, that means we're 1 unit closer than where we were before. We're going to see that same line, or almost that same line, but it's been shifted up 1 unit. So when x is equal to 1 and y is equal to 1, then our z value would be equal to 3 rather than being equal to 2 like it was over here. So we would go up 3 units. It is really hard to draw. We do the best we can though. And when y is equal to 2, we'd see that, and x is equal to 1, z would be equal to 5. So I just keep drawing these little rectangular boxes. It's hard. No, we're not artists, not all of us. So those would go be on our plane as well. So this is really a horrible sketch of a plane, but it's going to look something like that. Oh goodness, it's really hard to draw. I will just say it kind of looks like this. Plane. And the equation of that plane is 0 equals x minus 2y plus z. All right, or you can put the 0 on the other side, that's fine. So we've got that is the graph of that equation. And this one involving the sine and cosine required us to use that Pythagorean identity. It turned out to be an elliptic cone. A couple of things I want you to notice, since this one involves cosine of v and sine of v, there are cross sections when it looks like when u is equal to a constant, which means that z is equal to a constant. Those are all going to be circles of radius u, or actually circles of radius z, because u and z are the same thing for different values of u. I guess that's true when u is positive, and when u is negative, they're going to be circles of radius absolute value of u. So that would be down here. So cosines and sines lead to cross sections that tend to be circles often. And then over here, notice that our u and v were just multiplied by 1/2 or 1. The coefficients were just constant coefficients, not integer coefficients, but just constant coefficients, and happen to have a rational coefficient there. But when I see something like this, I'm thinking plane, because we know planes have this form, have an equation of this form. They have equations that look like this: ax plus by plus cz equals d, where a, b, c, and d are all constants. So I see that and I'm thinking there's got to be a way I can put the u and v together, or make substitutions, excuse me, so that we put our x, y, and z together and it will look something like this. I don't actually know, just from looking at this, what the form of this equation will be, but I can see that if x equals u and z equals v and y is equal to just some constant times u plus a constant times v, this should work out just fine. Sorry about that. Little issue with my camera. So everything just turned off all of a sudden for no reason. Okay. So that is that one, and let's do the last one. It has another cosine and sine in it. Oops. R of u and v equals v times I hat plus cosine of u times j hat plus sine of u times k hat. I prefer to write it like that because it's shorter, but WebAssign lists it for you this way. It's the same thing. I would identify my x, my y, and my z. There's my x, there's my y, and there's my z. That's my x component, y component, and z component in terms of u and v. And I see I've got cosines and sines again. This time I've got cosine and sine of u. Since both of those angles are the same, we can use our Pythagorean identity again. We know that sine squared of some angle plus cosine squared of the same angle is 1. So in this case, if we substitute, we know that sine of u is equal to z. We can sub that in. And cosine of u is equal to y. That's true for any angle A, but it's also true for u, obviously. So now I've got this z squared plus y squared equals 1, or I prefer to write that with the y first. It's just traditional to list those variables in alphabetical order when we can. So you have x or y squared plus z squared equals 1, which in the YZ plane is going to look something like this. Oops. There's z and there's y. We'll see a circle of radius 1, centered at 0, 0. But x is free to be anything. Now remember, with our coordinate system, we tend to look at it like this, where we're imagining the x-axis is coming out of the page. The y-axis looks like it's going to the right relative to us and relative to this perspective, and z is going straight up. So the YZ plane is actually back here. It's this plane in the plane of the page. And that is what we would see in the YZ plane. But this is true no matter what x is. Here, x is free to be anything. So this is a cylinder. So we'll have y squared plus z squared equals 1 when x is 0. We'll have y squared plus z squared equals 1 when x is -2. So I would see that same circle back here. Isn't that what the press secretary always says, circle back? And we'll see some circle forward over here. Never heard her say circle forward. There we go. But x is free to be anything. I can't draw the whole thing, but x would go from -infinity to +infinity, and we would have this cylinder. So that's what we might see, like that. Of course, on the inside of the cylinder, we would also see that. Maybe the inside of the cylinder is red. It's kind of cool, adds some visual interest. Okay, so as I'm going through this, if you're saying to yourself, how would I know to stop here? I would know I just found a relationship between y and z that must be true no matter what x is. And then I look over here and I see that x is equal to v, and we were not given any restrictions on v. We weren't told that v starts somewhere and ends somewhere else. We also weren't given any restrictions on u. So that means we get the whole cylinder. Now, as we move into evaluating surface integrals, we are going to have restrictions on u and v that'll tell us which part of this cylinder we're actually interested in, which part of that cylinder is our surface. We discussed those in class. As you prepare for exams over this material, make sure you're comfortable graphing a part of a surface associated with particular bounds for u and v. But for this homework problem, I think we're pretty much done. This last one was the cylinder, and the first one was our elliptic cone. It's actually a circular cone. centered at 0, 0, 0, or you can think of that vertex. I think that's what we call it, as a vertex of the cone at 0, 0, 0. And this is a very bad, poorly drawn plane. So let's go back to the homework assignment and see that those graphs are on there. So for this first one, we have u times cosine of v times I hat plus u times sine of v times j hat plus u times k hat. That turned out to be our elliptic cones. That's our answer. This one, a y squared plus z squared was equal to 1, and x was free to be anything. And that is that graph. Notice they've got the x-axis going off to the left to make it easier to draw. And then, oops. And then this one, where x is equal to u, y is equal to u times the quantity u plus v, and z is equal to v. That was the plane that I was having such a hard time drawing. And it's sketched right there. So remember, guys, as you are preparing for exams, you will not have a matching problem like this. You'll actually have to graph them yourself. So you want to get comfortable using your Pythagorean identities to eliminate those trig functions, and then thinking about ways to relate x, y, and z by eliminating the variables u and v. Often we're just making substitutions, except for when we've got those trig functions.